today we complete our kinematics consideration of the module 2 kinematics by discussing a rigid body motion, which is a very important one, and the related to that concept of objectivity of our vectors or tensors. Now, so the motivation to introduce a rigid body motion and consider it a little bit with in more depth is that so we're not doing this today, but later, as we want to introduce the material law, constitutive law, so meaning the relations between stresses and strains in certain manner, we want this to use such a tensors and vectors, or in our definition, such that the result of our constitutive law, of our material behavior, will not change if we have a rigid body motion, right? Because rigid body motion, we have not defined it just yet, but this is something that is not strictly related to the deformation of the material. So the relative position of the point in the body do not change, although the whole body can move, and hence the as if it is rigid, so not deformed, and hence the name of rigid body motion. Now, so with that in mind, so we want to talk to objectivity, about objectivity of our measures. So let's first look into more specifically what we mean by how we can define the rigid body motion. Okay, and so here's our schematics of these typical potatoes that we start from the undeformed configuration. So, and as before, we had the position vector x. So okay, let's have 2 points because we want to define a vector, some arbitrary vector between that is defined by these 2 points. And so very typical, so now after deformation, a general deformation gradient f can be anything, so we don't restrict it beyond the usual restrictions about the determinant that is positive of f and one-to-one mapping from here to here and back. So this potato or this body is deformed, undergoes some deformation described by deformation gradient f, and each point here goes through the mapping depending on this deformation gradient at each point. So our vector x1 goes to y1, and our point that is described by the vector x2 goes to the point that is described by y2. And so then here we focus on this deformed configuration, and we superimpose or additional rigid body motion on this deformed configuration, right? Remember, so even the deformation gradient we could split into a sequence of deformations, and we decided to do this through the first stretching and then rotation tensors. So and also so we can just keep doing that and continue deforming that. But now here from this configuration, from the current configuration, we apply a rigid body motion that we described by the tensor Q, different from general deformation gradient f. And now the result of this superimposed rigid body motion, so we denote everything by star as we go from here to here by the mapping tensor, second order tensor Q, again rigid body motion. And so we have a point associated with the position vector y1 going to y1 star, and 2 going to y2 star. And so, and now, so what we also will do, we will follow this vector s, and what it changes this vector undergoes from going to here to here. So now we are not interested in how that vector changed from here to here. We considered that, so we defined the lengths and angles. So now we consider this situation when that vector, an arbitrary vector that is defined by 2 points, changes upon when we apply a rigid body motion. Now, so again, so that any vector that y1 or y2 is obtained by mapping its correspondent original vector here. So y1 is mapped by q into y1 star, and y2 is mapped into y2 star. So the q needs to act on these vectors, and hence so we can write that new vector will be y star, that the new one is obtained by the mapping of q on y plus some constant, because well, they if all the points move the same distance, so without undergoing rotations, so then linearly, so then you can also add some constant, some arbitrary constant here, and still not exerting deformation, still will be rigid body motion. Now, what is our vector q? So q is again is a proporthogonal tensor. When we say proporthogonal, we mean that the determinant of that of q is 1, so, and it's more than 0, so this is positive, and that means that the material in this mapping will not disappear. And also q is describing rotation, right? So, and this is the properties of the of the proporthogonal tensor, is that the transpose of that is equal to inverse of that vector, right? So if we multiply it with itself, then we obtain identity tensor. If we multiply with transpose with q, it will be exactly the same as multiplying the inverse part with that. Now, so now we're going to look into the changes of S into going into S star after rigid body motion. So we need to make sure that the length doesn't change, right? So if it is a rigid body motion, we expect these vectors do not change the length, right? So it's any vector here, right? So the arbitrary vector between arbitrary choosing 2 points, so the length need to be the same. Another parameter that we had before was the change between the angles of 2 vectors. So we could define another vector in the same manner, and then follow the change in the angle between these between two fibers, right? So we can do that. So this is what we are going to look into, right? So we're going to look into the change of the length of an arbitrary vector that is undergoing rigid body motion from the deformed configuration, and then we will look into the change of the angle. Now let us calculate the length, and so the length will be calculated as the dot product of S star, right? And then we can compare it to S. And S star is nothing but, again, we can conclude from here. So so this is just a little bit more of things that we have here. So S star is the vector that is the difference between these two new position vectors after rigid body motion superimposed on the deformed state. And so each of these we could write as qy2, for example, minus qy1. So we pull q outside, and we have this q acting on y2 and y1. And so, but this is of course nothing but y vector S. So whatever is the parenthesis is the that original vector S that we found in the deformed of the current configuration. So we can write that the new vector S star is nothing but this qs. But no, this is a straightforward operation here. Now, we're going to calculate that length of S star. So we calculate the dot product, and then don't forget to take the root square of that. And so now we can use this 253 to substitute it here with the one. So basically what we want to do is to write it in this way. right, so we are writing S star here dot product S star, which is basically multiplying again by using 253 as QS dot product QS, and right, and so which is also a vector, like you can have parentheses here, and so what we want to do, and you can see it from here, is that we want to have these Q's multiplying each other, so we want to unite them. So, and then we can use that trick that we did before, and you can do this exercise one more time, is that we can rewrite what is here in the left part, in this left parenthesis, as S multiplying but dot product here Q transpose, right? But it's important to have a transpose, because here, if you think about it, it's an index notation again, so then you have here I J as J, and so you need to make sure that that J that was in S is still multiplying the right index here, right? So that, and hence this is a transpose. So then we'll have this Ij, but that would multiply the first one. So that hence we have this Ij like this, and then you transpose that Q, moving that. We're changing the order here in transposition. So that's as we define the order. So this is just because our agreement of how the multiplication works when I have this dot product. Okay, so we already considered that, just a reminder. And so then the second part is not changed, and so we have still this Q QS, this is the vector. So now what you have here, if you look into this whole thing in one more time, here, so you have this QS, which is a vector, then this Q transpose, okay, let's put it here, the parentheses, so this is a vector, so then this Q transpose acts on that vector, so this is another vector, and then it multiplies this dot product with another vector, so it's still a scalar. But now what we can do, we can actually look into this part and recall that that was our property of this orthogonal tensors, Q or rotation tensor, that when we apply Q transpose Q, it's nothing but the identity tensor, right? And so then we can use that property here. So we can write, okay, so we see here that we have this Q transpose Q, so this is nothing but identity tensor, and therefore, right, so this is, but the identity tensor acting on that tensor S, so it's still vector S, and we obtain that the result is S dot product S and root square, and so of course this is the same initial length S. So we obtain that basically the length after the rigid body motion is the same as the original length of the same vector in the deformed configuration, as we described that as we defined it in the deformed configuration. Now next thing for us is to look into the angle, and so we just can for that we can define another arbitrary vector p and measure the angle between that vector p and the vector s. Both of them, of course, are randomly chosen, and that should work for any of these pairs of vectors. So let's calculate the change in the angle. All right, so and again, so for the angle, we're not calculating the angle alpha itself, but rather we're looking into the cosine of alpha. But of course, you can calculate the angle if you want. But for us, it's enough to establish that cosine alpha of the new angle, the relation with the original angle. Okay, so we can write it again. So it's nothing but the projection of one vector onto another, and hence we have this dot product normalized by their lengths, because they are not unit vectors, right? So this is the length of new vector S star, and this P star. And S star we had in our schematics, but P star, okay, so it can be any other vector that we can define the same manner as S star. Again, P star is also obtained by rigid body motion from the deformed configuration from an original vector P. Now with that we can use again 253, and we can write in a similar manner as we wrote just in here, that we have S star multiplying P star. So basically we write exactly the same, it's just the only difference that instead of the second S we'll have P, because of the different because we have a multiplication of P of this P obviously here. So we still use 253 for S. Okay, it's straightforward, that was exactly the same notation, QS. And now it multiplied, so in but of course this formula 253 works for any vector, so it's just okay, random choice of the name of that vector. So we can write easily the same P star and P here, so hence we can write Q multiplied by P. And as we continue we'll basically use exactly the same trick here, because we want this Q to be together, so we can combine them very conveniently into identity tensor if they come with the right transposes, right? But we already know that that's exactly what will happen, so we'll change the order here, so it will be S multiplying Q dot, and that, oh, Q transpose, sorry, and that Q transpose is acting on the vector. Okay, so you can ignore this dot here, so I can okay, so that we don't write dot typically when we multiply when we act with tensor on the vector, so it's still correct. And so therefore again here as Q transpose is identity tensor as we just discussed it here, and so we can then continue writing that this is nothing but S multiplying P. Okay, so with that we can continue here. Just to write it in our formula. So again, so this multiplication S star and P star is nothing but S multiplying by Q transpose QP, this whole tensor that is vector that is obtained here, and we already know that Q transpose Q is identity tensor again. So this is our proper orthogonal tensor. That's the property of that. The Q transpose can be expressed as inverse, and of course then automatically this is identity tensor. Then you act with that identity tensor on vector P, and of course the return of that action is the initial vector P. So we have SP, S dot P, again projection of these vectors onto each other, and they are normalized by their lengths. So this is exactly the definition of the cosine of the angle between them. So and we established through here that indeed here the angle remains the same when we apply a rigid body motion. So the length preserves and the angle also preserves. And so the length we established it here in 244, and this is the change in the length in the angle. There's no change obviously when we apply a rigid body motion from the deformed configuration. Now it's important to note again that basically now we're saying, okay, so any vector that obeys this equation 253 basically that is obtained equivalent to the this action of this proportional rotation vector q, then the vector we call it objective. And it's important for us to use objective measures when we try to write our constitutive law, because of course we don't want to any measures of stresses and strain to be changing as we have rotation, because essentially the state of stress doesn't change and state of deformation at a point doesn't change with that. However, interestingly, you would think that might think that this is not an issue, and so it's somewhat straightforward. However, not all vectors are objective. In fact, the vectors that are very familiar for us are definitely not objective, and we're going to look exactly into these vectors. Particularly, we're going to look into the our familiar velocity and acceleration vectors, which are not objective. In simpler words, let's say that when we say that if the vector is objective, is that it's unaffected by rigid body motion. So otherwise it's not objective if it is affected by the rigid body motion. Okay, so let us start from the velocity, right? So that's and the velocity vector in the after the rigid body motion, so this v star is defined as a dot product, right, or time derivative of that vector u star in the after rigid body motion. So that's stuff. Now we can also write that position vector y star as through our definition that this y star as a result of rigid body motion from the deformed configuration y is obtained by the mapping with the proper orthogonal rotation tensor q on y plus additional constant of linear displacement of movement of all the points without the rotation, just the rigid movement. And so then we take this 241 and simply substitute that instead of y here in the parentheses, and then we just take the derivative with respect to t, because that's basically what dot represents. So and now we're calculating that v star, so that we want that v star to obey 243. So v star would be equal to qv. If that's the case, then we can say that the velocity vector is objective. If it's not, well, then we'll need to say that it's not objective, so that is affected by the rigid body motion. Now, so what do we do here? Okay, so we'll just simply take the derivative of each of these terms, and basically, so this term, when we take the time derivative, will produce us two terms. The first is q dot y, and then the other one will be q multiplied by y dot, and we have c dot as well. Right, and so then next we can go back to 241 and we can rewrite the that we can rewrite that y okay as we can use 241 to substitute it. Y is in here, right? And basically, but y will be nothing but this, because we can just take that c with the minus, pull it to the right, to the left hand side, so that will be y star minus c, and then we will need to multiply everything with q inverse from the left, and so we'll have y on the right hand side, which, okay, we change the order here, moved it on the left hand side, and the rest of the right hand side, but on the other side that will be q inverse multiplying y star minus c, exactly what we have here. And so, and now we take all this and substitute it here. So we obtain q dot multiplied q inverse and y star minus c. So this term actually, so then we'll write this term. So now if we look at this term, so that will be nothing but qv, right? So this is by definition uy. So basically, and that would represent the part that we are looking for, because in 243 what we were looking for is that v star will be equal to qv, and if that's identical, that holds true, so then we could say that the velocity is objective. Now so we have this term, but we also have these extra terms, and only if these extra terms will be zero, only then we can say that the velocity vector is objective. So, and basically we have so we have this and this term that are kind of extra. They don't allow us to claim the objectivity unless they are zero. Now in general they are not, and so here we also can introduce the so-called spin of rigid body motion. So this q dot q minus 1, and which well, can be written. We still remember that inverse of q can be substituted with transpose, and so so there is a certain property of that. So this is a spin of rigid body motion. Okay, so let's write it somewhere here. Spin of rigid body motion, and this is an antisymmetric tensor, and so which is hard to see from this definition, but need to do some additional exercise with that. So again, so the first one that is that we, instead of the inverse here, because this is still proper orthogonal tensor, we can write that this is a q transpose, which we do exactly here, right? And now we can look into this term and with some trick we can say that spin is the antisymmetric tensor. So and that's what we do exactly here. So we have a dot product time derivative of this q transpose, which we know that that will be identity tensor, and so if we take the dt time derivative of the identity tensor, we'll obtain 0, right? So which we have here, but now the components of that inside, so we can look into that. So there will be q dot multiplied by q transpose, so that's exactly the first term, and the second term is q transpose. And so you can see that this q dot q transpose, which is exactly here, is equivalent. So because from here we can conclude, we can write that this q dot q transpose equal to minus q dot transpose. And now you can notice that if we apply a transpose operation of this guy, so we actually obtain so that will be exactly the transpose of that. This is minus. So if we transpose this, so we'll obtain that q will go here, right? So if we now so the transpose of q dot q transpose, right? So the whole term from here, right? So if we apply the transpose to that, to this term here, so then what we obtain is so they change the order, and then transpose will be q, and then we'll have q dot transpose. q dot transpose. And that's exactly what is written here. So we can say that that actually was exactly our spin omega, right? And so this is exactly omega transpose. So then we can conclude from that well, yeah, so that's the spin of the rigid body motion is theta is equal to minus omega transpose. So this is the antisymmetric tensor. Okay, so nevertheless, so we're now going to back to this result here when we still try to locate conclude whether the velocity is the objective vector. So now we write it more complex. Instead of q dot q minus transpose, we use our definition of spin of the rigid body motion, and so rearrange it a little bit. So put qv first. So we have this qv plus theta y star minus c plus c dot, and so here we can see that again, writing this is here once again exactly the same thing, is that in order for v to be objective or to obey 243, we need to ensure that this term is zero, but unfortunately there is no way that in general that term will be zero. So therefore velocity vector is not objective. Now we can follow a similar procedure for the acceleration tensor, and so the basically now once we have this formula for v star, so now the acceleration is the just we need to take the time derivative of the velocity. So in a star will be time velocity of v star, and then we can continue taking this. So we basically would substitute this term here, take the velocity dt product of that, and then so one of the terms that will be as qa will appear here, and we would hope that all the rest that comes out of this derivation would be zero. But unfortunately, again, similar to the velocity vector, acceleration vector, this term in general is not zero, and so the acceleration vector is also not objective. It doesn't obey 243. We cannot say, so we couldn't say here, and so the a star also the is not equal to simple mapping of acceleration vector by the rotation by the proper orthogonal tensor q, and therefore they are both not objective. Alright, so now after defining things and illustrating for objectivity terms for vectors, let's go after second order tensors, and that's probably even more relevant for us. It's again the motivation after that is to identify the the constitutive law, to postulate the constitutive law that essentially will relate a second order tensor such as stress and strain. So, and we don't want that to be affected by rigid body motion. That doesn't really cause a change in, should not cause a change of the state of stress at any point, or deformation state. Now, so we're going to look into second order tensors, and the objectivity of second order tensors defined through the vectors. Basically, what we are saying is that again, and what is tensor? So one way of looking into tensors is that is an operation, so mapping of vectors. So therefore, we define the objectivity of a second order tensor through vectors. Now the vectors, let's say the vectors are objective. Now so then we can say that the second order tensor is objective if, when it acts on those objective vectors, the objectivity of those vectors is preserved. So again, so that, let's say we have a second order tensor which is nothing but something that acts on a vector. So we take that vector and apply it to objective vectors, right? And so then we see that the result of that is the new vector, right? So this again, so this is our second order vector A. So it acts on S and produces a new vector R. So it's in action. So now let's say we know for sure that these S and R are objective, right? So S and R are objective, so they obey our old formula 243, right? So that can be obtained back through the formula that multiplying that simply by the proper orthogonal vector Q or tensor Q, and so this vector A will still be objective if once we act with that A on S, and it will so the objectivity will still be preserved. All right. So now what we're saying is that, okay, so that can be written so that right, once again, so A maps that objective tensor S into objective tensor R. So these are R and S still defined in the deformed configuration, and A is also defined in the deformed configuration. Now that after rigid body motion, all of them, this mapping should look like that. When we have this rigid body motion superimposed on the deformed or current state. Now, now since we know that R and S are objective, so we can use the 243, our previous formula for them, and so we can write that R and is equal to R star is equal to QR, and S star is equal to QS. Right, so that's basically, this is because S is objective. Just write it here, and R is written here, and basically we use that 243 formula for any vectors that are objective. So that is what we got here. And now now with that we can go ahead and we can rearrange our formula a little bit. So what we are going to say here is just, okay, so we can basically we can multiply that left hand side with the inverse Q or with transpose, right? So we can if we do that, so that will be Q transpose here and Q transpose here. So we didn't change anything to 60 really, and then of course we remember that this is proper orthogonal tensor Q transpose Q that will produce as identity tensor, right? So then when we act with identity tensor on R, so the result is that we still have R. So we can write that R is equal to Q transpose A star QS. All right. And now we can identify here this block, right? So this is what is inside here, the Q transpose A star Q, and so basically the second order tensor, second order tensor, second order tensor. So this multiplication of this another second order tensor, and then that will be also second order. So this is still a second order tensor. Now we also can note that we had initially that in 248 that will be our A. So if R and S, so they're still objective, so the straightforward, the A that maps them will be equal to this term, because, well, that's exactly what 258 here. We have R here, S and S multiplied by second order tensor here. And this is the same second order tensor, so they must be the same. And so basically in that sense we arrive to the definition for the second order tensor objectivity. So the second order tensor will be objective if it satisfies this condition. And note that we have this and this is for again for the tensors defined in the deformed configuration, right? So so we have this double multiplication Q and Q transpose from the left and right. And this is also familiar for you, of course, as you when you try to rotate second order tensor, for example, stresses, then that's how you do that if you want to rotate it in a different configuration, different coordinate system. So this is similar operations that you apply here. So once again, this 262 is our condition for second order tensor, objectivity of a second order tensor. Now, okay, so we're going to look into examples of some second order tensors that we already defined, that have some interesting physical meaning for us. And one of them is the so-called velocity gradient, right, that we just defined previous lectures. So let's look at that and see if velocity gradient is objective. Again, so we know that the velocity itself is not objective. So let's see if the velocity gradient is objective. We also have the deformation rate, which is also interesting to see if that will be objective and which of them will not. All right, so let's okay, so this again, we're going to look into some examples of the our usual suspects of our known second order tensors. So we'll start from the velocity gradient. And so again, 262 is our condition for the objectivity of a second order tensor. Now, so basically, so our velocity gradient, so we need to multiply it with Q and Q transpose from left and right respectively. So, and then if that so then that will be our exercise that we want to produce here. Now before we proceed, would like to note about the the deformation gradient, which is also second order tensor, but is a little bit different, as we said, is a 2-point tensor, so it's not defined in the deformed configuration. Therefore, it has a different objectivity condition. So it's so the rigid body motion produces a little bit different result on that. So to illustrate that, let us look into that. Just write, let's say here for deformation gradient, so the deformation gradient after rigid body motion, right, so F star will be still, so we use the definition deformation gradient as a grad y, but because so when we look at the position y, so now this is star because, well, that's after rigid body motion, so we're looking at F star. Now with that we can recall the definition for y, all right, because in that configuration after rotation, so that will be, so that y will be grad, right? So but now instead of y star I will have qy, right? So that is the mapping of that y into y star rotation plus c, right? And c is independent, so it doesn't really change with the position vector, right? So when it takes the derivative, so grad c will be 0, and so and q, of course, the rotation also is not is independent of the position, so we can pull it outside, so that will be q grad y, but then grad y is nothing but f. So so we can write that we have so f star is obtained by mapping, so by applying that proper orthogonal rotation tensor q on f. So don't have this additional, so it does work differently, right, for this 2-point tensor that is defined in these two configurations. So this is for AF star. Now now we're going back to 249, and we are going to calculate what is that L star is. So that L star is nothing but the what had here, so we just need to put star everywhere here for F. So F dot star and F star inverse, right? So it's 249. Now here we are going to basically to use what we just derived for F star, right? So because it's QF, so we substitute this in here, right, and take dot product, and so what we obtain is Q dot F, right, the first term, and second term is QF dot. So it's with the multiplication, so we have two terms when we take the time derivative for dot operation. And now when we apply it in here, so this is an inverse of QF, so that will be so we put that inverse everywhere here, but we don't forget to change the order of multiplication. So so QF inverse will be F inverse multiplied by Q inverse. Now so with that we can go ahead and actually to apply it here in on these two, and so and when we multiply it with first this here Q dot F minus Q, so the first multiplication is Q dot F, writing this explicitly, F inverse Q inverse, and you can notice that there is F multiplying F the inverse deformation gradient, and of course this multiplication here produces you the identity tensor, and then you can apply the identity tensor on Q inverse, and that is still will produce as Q inverse. So the first term is nothing but still having Q dot Q inverse, but that what we already said, this is we define this as a spin of rigid body motion, that omega. Right, so we can call the first term will produce as omega when we multiply this with F inverse Q inverse, and then the second term will be okay. So we'll have all these four multiplications, and the only things that we can note here in the second one, so the result is here, right? So the second term, so that will be the first term, right, and that the second term, and so the second term here. What we have, I'm just copying that QF dot F minus 1 and Q minus 1, and then and then we can note that actually now here these two guys are nothing more but what we see here in 249. This is the velocity gradient L, and so we can write that this is we continue, then this is our Q L q minus transpose. So if you want, you can write it so it's not minus transpose but q transpose. And this part is good for us, right? So this is exactly what you would want if you look at this 262, the objectivity condition. So we have two terms, so that L after the transformation is, again, this is spin that we obtained here, first term. Second term is QL Q transpose, or minus 1 is exactly as being transposed. So again, so if that spin of rigid body motion was 0, then yes, we could say that the velocity gradient is objective. However, it's in general is not 0, and therefore we can conclude that velocity gradient L is not objective. So L is not objective. So velocity gradient is not objective. It has additional term. This one is not objective. Right, so this because of this term. Okay, so now what we can do, so let's just note that and then show an example where we might be more lucky. And so this we are going to look into deformation rate, and so which is in fact composed of the velocity gradient components, right? So this is the symmetric part of the velocity gradient, so the deformation rate. Now here it will be an easier job because we already calculated L star, right? So that's basically we can just use the results that we already calculated, right, and see what we can obtain here. Right, so so we can write that D star is nothing but half of L star plus L star transpose, and but so L star we already wrote here, so that will be nothing but exactly what is written in 264, right? Oh, T263. So that's exactly will be omega plus QL Q transpose. Okay, so instead of inverse, we will just write transpose. That's what we so because we know that Q minus 1 again, right? So the inverse of Q is Q transpose. I'm just reminding you again. And then the second term here will be the transpose of that. So we'll have okay, so we'll have the spin, rigid spin transpose theta transpose plus, and we will need to transpose this whole thing here. So we'll have so the okay, let's write here that L star transpose, right? That will be, if we take it 263 and transpose that will be the spin transposed, and then we'll need to transpose this whole thing. So we can do this in the following way. So we can just say that we treat that. Okay, so let's write this. So we have this Q, and let's put parentheses here just to make it more clear. And again, instead of inverse, I write transpose here right away. And so now we need to transpose the whole thing here, right? And so I deliberately added here these two parentheses because I treat that ALQ transpose as another second order tensor, right, just to follow this transposition rule, right, because L multiplying Q transpose is still second order tensor. So now this second order tensor, this in parentheses also second order tensor, so transposition is quite straightforward. So I can write that as L Q transpose, and I still need to transpose this tensor that obtained as multiplication multiplied by Q transpose. Multiplied by Q transpose, and then when I transpose that, I will have Q transpose transpose, which is Q multiplied by L transpose, and then I multiply that by Q transpose. So this term is nothing but this term here. And so then we can substitute that L star transpose right in here, right? So that these two terms, they are coming in here, and then we obtain. So this first is that our original L star, right? So just change the order. And this is our second term that that is L transpose, L star transpose, right? Now, what is important to note here is the property of the spin of rigid body motion that's antisymmetric, and actually theta is equal to minus theta transpose, and it becomes very useful and important for us in this situation. And so we can say, okay, so if that's the case, so that instead of that I can substitute minus omega, and so these two will disappear, and then I can know that actually what happens here, I have a term L and L transpose here that are multiplied similarly by Q and Q transpose from the left and the right respectively. So I can pull this multiplication Q and Q transpose out of the parentheses, so that Q will go outside of the parentheses here, and that Q transpose will go outside of the parentheses to the right, and that Q again going to the left. And then I can basically write that, okay, so this is Q that multiplies from the left, and this Q transpose multiplied from the right. And again, if I pull them in, that Q will multiply this and that guy, and that Q will multiply this and that guy, but from the left. And so I'll have these two terms again, back again. And then I can note that what is very good for us here, that this is nothing but D is the deformation rate. So that's exactly how we wrote the definition of that. So this is it's half L plus L transpose. And so, and at the end, very surprisingly, we obtain that the deformation rate is indeed objective, and it's very good for us. So this is because that actually exactly obey this 262 condition for objectivity of second order tensors. So also again, partially as a surprise, it can come from the second order tensor basically built on from certain components, from certain structures built on the velocity gradient, which we did see that it was not objective. But as you see, because this transposition, so this term, this spin of rigid body motion, theta, was eliminated at the end because of the transposition, because of certain structural deformation rate. So we were able to eliminate that spin of rigid body motion and show that the deformation rate is indeed objective. So it's not affected by rigid body motion. So, and at the end, so let us conclude this discussion of objectivity by important notion that even so the second order tensor is objective, the rate of that objective second order, and when I say the rate, is meaning that the change in the so when we take the derivative, so that the what we mean by the rate, so the change in time is not objective, and so it can be easily seen from here because let me just erase this because they're not helping us. So it can be seen here as we take the derivative, the dot operation of this objective second order tensor. So okay, so we take that, so we produce three terms, obviously. So okay, we can again split in our more convenient and do this by step, by step. So as if we have two tensors, because this AQ transpose can be seen as another second order tensor, and so then we have Q dot multiplied by AQ transpose, and then we have Q multiplied by AQ transpose dot. So this is the second term, and then we need to take the dot of AQ transpose when both of them will be multiplied by the Q here, right? And then of course that will when we take this dot product of AQ transpose, then we have A dot Q transpose plus A Q transpose dot. And then if we look into that, so we can notice that, well, yes, so this one that I marked in blue here would be so that represents that objective part of that, but there are unfortunately these two terms that in general are not zero, and these terms are those that prevent us from saying that the rate of the objective second tensor is also objective. So it is not, and therefore there was a development and a need to postulate objective rates of second order tensors, which are not going in depth and just giving these examples of objective rates that were proposed with different names, and as Zaremba Juman objective rate of a second order tensor, Truesdell and Oldroyd. We're not going to look into much details into that. I'm just pointing this out, and for more detailed discussion of that and more rigorous definition, we can look into the excellent but rather challenging reading on the topic in the book by Cliff Truesdell. All right, so with that we finish our consideration of kinematics, and we'll go to the third topic of module of our course. So we're going to the balance laws, which are very important. So now we are prepared to go there. All right, see you then.